In information retrieval, one of the challenges in learning a good dense vector representation is that, unlike positive examples which are usually given, negative samples should be selected from a large pool of data. One option is to use BM25 and retrieve top passages or documents that actually don't contain the answer but still match most of the keywords in the question. However, this approach might cause the dense retrieval model to just mimic the base model, such as BM25, and actually does not push the performance much beyond the base model, especially when it comes to document retrieval. Another option is to use in-batch negatives, as the authors did in the DPR paper. However, in the ANCE paper, the authors showed mathematically that using in-batch negatives can lead to diminishing gradient norms, which causes high variance in the stochastic gradients and slows down the training convergence. As a result, the experiments show that in-batch negatives actually don't perform much better than BM25 negatives. Another option could be to find global negatives from the entire corpus and use those for training. Directly retrieving global negatives from the entire corpus using an optimized dense retrieval model and then using them to train the model can be an effective approach. As you can see from the figure, random or BM25 negatives are pretty different from the global negatives. The main challenge here is that you should keep an up-to-date index to select fresh global negatives while training the data. To maintain an updated index, 3 steps are needed. First, in the inference stage, you refresh the representations of all documents in the corpus with an updated dense retrieval model. Second, in the index stage, you rebuild the index using the updated representations. Finally, in the search stage, you retrieve the top documents from the index for each query and sample negatives by excluding the positive documents. The second and third stage, building the index and searching for negatives, can be efficient when using tools that are made for fast similarity search, such as FICE. The bottleneck in this process is the first inference stage, which is too costly to compute for every batch. It involves performing a forward pass on the entire corpus, which is significantly larger than the training batch. As a result, it is almost impossible to maintain an up-to-date index to select fresh global negatives at every step. To address this issue, a novel method called asynchronous index update is employed in the ANCE paper. First, in ANCE, inference runs using the latest checkpoint of the dense retrieval model, let's say checkpoint K, to recompute the encodings for the entire corpus. At the same time, the trainer continues its stochastic learning using negative documents retrieved from the index created by the previous checkpoint, which is checkpoint K-1. This training process runs in parallel with the inference process. Once the inferencing is finished, the inferencer updates the index for the entire corpus using the new vector representations. And finally, with the updated index, ANCE negatives are updated asynchronously to catch up with the ongoing ANCE stochastic training. And because the inference and the update of the index occurs asynchronously with the training process, this actually makes the whole training more efficient. The table above presents the experimental results. As you can see, ANCE outperforms most of the baseline models across 3 different datasets. For more detailed information on this section, you can refer to the paper. What I want to emphasize here is the efficiency of ANCE. The table provides a cost comparison between ANCE search and training and the BM25 method. As you can see, the total inference cost of ANCE is significantly lower than the sparse IR total, which combines the cost of BM25 retrieval and BART re-ranking. In ANCE training, the majority of the computation is spent updating the encodings of the training corpus using new checkpoints. The results shown in the table were obtained using a single V100 GPU. Although 10 hours for inference is substantial, this cost can be reduced by employing asynchronous index refreshes and by using multiple GPUs for training. What I want to talk more about is the hyperparameters that are used in this asynchronous training and the whole training quality. These hyperparameters include the frequency of index refreshing, the GPU allocation between the trainer and inference, and finally, the learning rate. The figure above illustrates how asynchronous learning behaves under different training configurations. In figure A, a large learning rate of 1 times 10 to the minus 5 causes fluctuations in the graph, as the asynchronous gap in the index can push the representation learning towards undesired local optima. A similar situation occurs when the refreshing frequency is too low, as shown in figure B, where the index is updated every 20K batches. This can also lead to instability in the learning process. Refreshing the index as frequently as every 5K batches, combined with a proper learning rate, results in smooth convergence as shown in figure C. However, this approach requires twice as many GPUs allocated to the inferencer, making it potentially less efficient. The authors of the paper explain that a one-to-one GPU allocation between the trainer and inference, combined with appropriate learning rates, is sufficient to minimize the impact of the asynchronous gap. Today I discussed the asynchronous index updates used in ANCE, focusing on how they actually work and some training details about the whole process. And that's all for this video, and thank you for watching. I'll see you in the next video. Bye.